Guys, welcome to our video on Math Review 1. This is actually going to be a series of 3 videos. We're going to do one video for each page of the Math Review 1 homework. This first video is going to cover the first sheet. The second video we're going to cover the second sheet, and we're going to have a third video that covers the third sheet. So let's jump right into it. The first problem says that the distance from Canandaigua Academy to my house is about 20 miles. Now, my house is Mr. Madden's house. If 1 kilometer equals 0.6 miles, how far is it to his house in kilometers? So we want to convert from miles to kilometers and show our work down here. Now I'm going to take a little bit of extra time on this first one to try and clear up some general things that we noticed as we were looking at people's responses. So the first thing I like to do with a problem like this is identify what my conversion factor is, and that's that right here, right? We're always going to be given a conversion factor in a problem like this, or we're going to have to know it, like some of the problems a little bit further on. But we're given our conversion factor here, and we have it from 1 kilometer to 0.6 miles, and this is a pretty standard format for a conversion ratio, right? We're going to have 1 of something to some amount of something else. Now, the reason that this might be a little bit confusing is you might not be familiar with what 1 kilometer feels like or looks like. You're probably more familiar with what 1 mile looks like. And so something you might want to do when you have a problem like this is try to identify which unit, right, which unit of the conversion ratio that you're more familiar with, and manipulate the conversion ratio, right, manipulate it so that it looks like something more familiar to you, right? Try to get the 1 for the unit that you are more familiar with. Now the way to do that is simply divide the two numbers of the conversion ratio. So I can do 1 divided by 0.6, and I can get that 1 mile equals 1 about, and I'll use the approximate sign, a squiggly equal sign, is about 1.66 kilometers. Now this probably makes a little bit more intuitive sense to you. You're probably more familiar with what 1 mile looks like. And this is telling us that every 1 mile has about 1.66 kilometers in it, right? So there's more, I need more kilometers to make up 1 mile. A kilometer is a little bit shorter than a mile, so I need more of them to make up 1 mile. So for our problem, we know that our original measurement of 20 miles, for every 1 of my 20 miles, I'm going to need to stick 1.66 kilometers inside of it, right, to do the conversion. So all I need to do from here is take my original measurement of 20 miles and multiply by my new conversion ratio. And I'll do it also the other way with the other conversion ratio to show you can do it either way. So we take our original measurement, 20 miles, multiply it by 1.66 kilometers for every mile, right, for every 1 mile. And this side I can make like a fraction too, and put it over 1 if it helps you visually to see that. You can see I have miles on top, miles on the bottom, those cancel. I'm just left with kilometers for units on top, which is where I want it. And this is going to be 20 times 1.66 is about 33.3 kilometers. Now, let's check if we do it with the other way with the conversion factor, with the 1 kilometer to 0.6 miles. Again, I start with my 20 miles, my original measurement, and I multiply by 1 kilometer for every 0.6 miles, right? Again, over 1, I have my miles on top and my miles on bottom. Now the difference here is my final arithmetic, right? Over here, my final arithmetic was 20. Here, let me highlight it here. 20 times 1.66, and that got me my answer. Over here, I'm going to do 20 divided by 0.6, and that's going to get me my answer, but my kilometers are still left up here, right? So I'm going to have 20 divided by 0.6, and that also gives me about 33.3, right? The same as over here. This was approximate as well. So the difference between using the two different conversion ratios is really just what arithmetic you're going to end up doing at the end. You're going to either do division or multiplication, and you can pick either one that makes more intuitive sense to you. I wanted to show you that you can change the conversion ratio to maybe make it make a little bit more sense. So let's stick our answer in here, 33.3 kilometers. right? And just like up here where it made intuitive sense to us that there's more kilometers in every 1 mile, our final answer has more kilometers than the 20 miles that we began with, which is a good check at the end to make sure we did the right thing. So now for part B, we want to convert our answer into meters, right? We want to convert from our bigger unit of kilometers down to our smaller unit of meters. And I know that there's 1,000 meters in every kilometer. This is a situation where we're not given our conversion factor because it's something we're going to be expected to know or be able to find on the reference tables, right? So we're working with the metric system. Kilo means 1,000. So there's a kilometer, a kilometer is 1,000 meters, which means there's 1,000 meters for every kilometer. So I simply multiply my answer of 33.3 kilometers by 1,000, which gives me 33,300 meters. All right, let's move down to section 2 here. It says, in lab, the length of a stretched spring is measured to be 5.6 centimeters. Convert it into meters, right? So now I'm going from, up here we went from a big unit to a small unit. Now we're going from a small unit to a big unit. And up here when we went from big to small, we saw that our answer for the big number, we got a bigger number when we converted it to the smaller unit, right? Now that makes intuitive sense. Take a second if you need to make sense of that. We had a number for our big unit and we converted it down to smaller units. We got a bigger number, as we would expect. It's going to be the other way here, right? If we have a small unit and we go to big units, we better get a smaller number than our 5.6. So just like kilo means 1,000 in the metric prefix system, centi means 100. So there are 100 centimeters in every meter. So all I have to do for this is take my 5.6 and divide it by 100. And that gives me 0.056 meters, right? See, I have a smaller number of meters compared to centimeters. All right, next one. The distance a ball rolls is 0.89 meters, big unit. Convert to centimeters, small unit. So now we're back to going from big to small, right? Centi, again, means 100. Let me highlight that for you. Centi is 100, and you'll find that on your reference tables. And so now all we need to do is take our 0.89 and multiply by 100, which gives me an answer of 89 centimeters, right? And again, this makes intuitive sense. If I had a measurement of some portion of 1 meter, 0.89 meters, right? Some fraction, some decimal of 1 meter, I'm going to fit in a whole bunch of centimeters into that portion of 1 meter. All right, next one. The mass of a collision cart is 234 grams. Convert it to kilograms, so small to big now again. So just like up here, kilo meant 1,000, down here, kilo means 1,000. So we need to do 234 divided by 1,000, and that's going to give me 0.234 kilograms. Okay, the mass of a spooky spring, don't worry, we'll get into what a spooky spring is at some point, is 3.5 grams. Convert that into kilograms, right? So small to big, and it's actually the same exact units as the last one. So again, we just divide by 1,000. So that's going to give me 0.0035 kilograms. All right. So the wavelength of a red laser beam is advertised to be 670 nanometers. Express this number in meters. So we're going from nanometers to meters and write it in scientific notation. Okay. So nanometers are really, really tiny. And that probably, you might not know exactly how much a nanometer is, but you can get a sense for it being tiny just from the wording here, right? The wavelength of a red laser beam. So wavelengths of light are invisible to us. They're tiny, tiny, tiny. And so we can make sense that nanometers must be really small. And we want to go to a much, much bigger unit. And we're probably going to want to do it in scientific notation. In fact, we're being told to put this in scientific notation. Because if I convert from something really, 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 really tiny to something much, much bigger, I'm going to end up with like 0.00000, right? If I wrote it out, it might look something like this. You know, a whole bunch of zeros and whatever my numbers are. You know, those aren't the actual numbers that's going to be, but this is the structure of what it would look like if you wrote it out in decimal format, which would be annoying for you to write, for one, and annoying for somebody to read because they have to count zeros to figure out what number you're trying to write. So that's kind of silly, and that's why we use scientific notation. So what we're going to do is check our reference tables and find out what nanometers means. Nano, you'll see, means 1/100000th. So what we want to do is take 6, and hold on, let me highlight for you here. So we're basically going to take our base number here, the 670, and we're going to keep it. And then we're going to look at the nanometer portion here, and this is sort of like our times 10 to the something, right? And we need to figure out what the something is. So this is the structure of working one of these problems, that you keep the base number and then you use the written description of the unit for the times 10 to the something, and the tricky part is figuring out what the something is. That's what you reference your reference tables for, right? So the nanometers, if we look, is 10 to the -9th. Now, if you've been paying close attention, right, you've probably noticed that this is not proper scientific notation, and the reason for that is because we have a 670 out here, right? We have a 3-digit number, and proper scientific notation has only 1 digit for our base number out here, right, our leading term. So what we want to do is probably, this is an okay answer, but let's make it in proper scientific notation. So to do that, I need to write 6.7 times 10 to the -7th. Now what did I do there? I moved my decimal point over 2 spaces, right? Made this leading term 6.7, and I changed my exponent because I did that. Now let me try to give you a little bit more intuitive sense of what I did there. I could write 6.7, right? And how would I get that to look like 670? What would I do to it mathematically? Well, I could multiply it by 100, right? And that would give me 670. I could also multiply it by 10 squared, which is 100, the same exact thing, gives me 670, right? Now this looks like scientific notation, because that's exactly what it is. So if I want to go from 670 to 0.6, if I want to go from 6.7 to 670, I have to multiply by 10 to the +2, right? If I want to go the other way, it's got to be a -2, and so we end up with 6.7 times 10 to the -7th as our final answer there. Alright, last one. So a typical resistor in a cell phone circuit has a resistance of 2.3 megaohms. Don't worry if you don't know what an ohm is at this point. It's a unit of electrical resistance. We'll get into that later. Convert to ohms and put in scientific notation. So we're going from megaohms to ohms, and if you check what megaohms is on your reference tables, you'll see that mega means a million, so it's a very big unit, and ohms is the base unit of electrical resistance. So this is a much smaller unit than megaohms. So we're going to have a whole bunch of ohms that fit into our megaohms, right? So let's take our 2.3, and then our megaohms is times 10 to the something. And if we check our reference tables, it's times 10 to the 6th because it's a million, right? 10 to the 6th is a 1 with 6 zeros. That's a million. Oops. And that is our final answer. All right. Hold on, I should add ohms to the end of this. I should have added, let's see, meters to the end of that. All right, that's our final answer, and that's the end of the video for the first sheet.